Okay, so there was some problem with this recording. So this is the second part. So I'm also discussing that. So I was discussing about the what should be the difference in third and fourth lines in rotational spectra of carbon monoxide, which are separated by 8 centimeter inverse. Okay. So you have seen that what I've said, that the difference between of energy between two successive levels is given by 4b. Okay. So 4b is nothing but is equals to 8 centimeter inverse. So you know by simple mathematics you can get this b as 2 centimeter inverse. Okay. So your answer is written here, that is 2 centimeter inverse. So it is your correct answer, that is 2 centimeter inverse will be your answer. So your total is 4b, which is 8 centimeter inverse. 4b, what is 4b? 4b is nothing but the energy gap between two successive lines. Okay, in terms of b. So from here you have got b. B is nothing but 2 centimeter inverse. So this is the answer. Okay. So I'm moving to the 11th question. I've added two more questions here. That the third and fifth line in rotational spectra of CO are separated by same 8 centimeter inverse. So you have asked what should be the expression of CO bond length. Okay. So you have to ask, you have to find what should be the bond length of CO. So your third and fifth line, as I have said, again I am writing this rotational Raman spectrum. So if it is the incident light, this is your first band which is coming at distance 6b. Okay. So next is 10b. To go with different j values, you will get 14b, get this will be 14b, 18b. Okay. So your third and fifth line, third to fifth line, what should be the representation? So delta nu bar will be equals to 4b plus 4b. So because from 3 to 4 there will be 4b, and from 4 to 5 there will be another 4b. Okay. So these two 4b's will make you 8b. So total delta nu bar will be 8b. Okay. So you have been asked that your 8b's would be equals to 8. Your 8b, your 8b should be equals to 8 cm inverse. Okay. So you know what should be the value of b? Be nothing but 1. But you don't you are not asked to find the value of b. You are asked to find what should be the value of r. That is what should the expression of equilibrium bond length. So if I write the if you recall what should the expression of b in the rotational spectrum, I am writing this as h by 8 pi square I c is 1. Right? This is the expression for b. Now you know what is I. I is nothing but mu r square. Right? So I am putting h by 8 pi square mu r square c will be equals to 1. Now what should be my r square? I am putting it here. So the h by 8 pi square mu into c. Okay. Now from here I get my value of r which will be equals to root under h by 8 pi square mu into c. So this will be my expression of CO bond length. Okay, this is a very clear cut calculation which is shown here, that what should be if the third and fifth lines in the rotational Raman spectra of CO is separated by 8 centimeter 8b or 8 centimeter inverse, how should be the expression of this bond length. Okay, so actually if this b value will, if this r value is dependent upon b, so for homonuclear diatomic molecules, if you know what should be the separation in the Raman spectrum, you can easily get what should be the bond length, what is the equilibrium bond length for this homonuclear diatomic molecule. So this is the advantage of Raman spectroscopy, which tells you that what should be the bond length for homonuclear diatomic molecule, which was otherwise impossible for other spectroscopic techniques. Okay. So your answer, you have got your answer. Your answer will be h by 8 pi c mu square. Pi c huge mu c pi square. Okay. So you have got your answer. So this is the expression for bond length of carbon monoxide. So this is the last question what I am going to discuss today, and this is a completely logical question. If you are watching this, you must give some attention to this. Suppose in a Raman spectra of a solution using yellow color laser light, we are getting both green and red color light as two peaks. If one starts heating the solution, which of the following is likely to happen? Okay. So you have been asked, that is, you are using a laser. Okay. Laser of yellow color. Right. You have asked that you suppose you are you are using some laser, and from this laser light is getting, and you have some solution. Okay. So from that is the scattered light. You scattered light, you will get two different kinds of light. Okay. One is green, another is red. Fine. So just let me explain that what you have thought, that is, we have some light source, and here light source is nothing but a yellow laser. Okay. So you have used this yellow laser. This is getting it is actually interacting with the substance present in the cuvette or something, a solution, and then you are getting two different kinds of color. Okay. One is a green color, another is a red color. Okay. So from that, it is if you are heating this solution, that means if I'm writing over here, if T increases, what should be the fate? Okay. So your question is, if you are increasing T, what should be the fate? Okay. So whenever these types of question you will encounter, so you can find this in also lecture number 38. This was discussed that, so you can clearly, what to say, match it, that is, your yellow light which has some lambda using in solution, there is scattering, two lights are getting, one is green which has different lambda. Suppose this is lambda g or prime, I lambda y, and this is, suppose this is red. Okay. So lambda r, suppose. Okay. So you are using lambda y yellow laser, it is an object, and from it you are getting green and red emission. Okay. In a red color at the two peaks. Now if you need to know the wavelength wise, in wavelength scale, which has the highest wavelength, green, yellow or red? If you see this visible spectra, if you see the visible spectra, you can see that your lambda g, that means the wavelength of the green light is less than lambda of yellow, which will be less than lambda of red. Okay. So it comes like nearly 500 to 540, nearly in this range. So green light actually comes as a wavelength of 500 to 540 nanometer. This has a wavelength of 560 to 590 nanometer, and red has a huge wavelength range up to 630, 620 to 650 nanometer. Up to that or something else in this range. Okay, so you can see here that your green light has lower wavelength than the yellow light, which has lower wavelength than the red light. Okay, now you recall what we have learned up to now. We have learned in a Raman spectroscopy, Stokes and anti-Stokes lines occurs. So if why I'm interested in Stokes and anti-Stokes, because I'm not interested in Rayleigh, because yellow color solution in Rayleigh, yellow color laser light will give you yellow color. Okay, so I'm not interested in Rayleigh. That's why, because your yellow color is not mentioned as the color is appearing from the substance. Okay, this is only the laser light. So I'm interested only on Stokes and anti-Stokes line. And for Stokes line, what happens, that your the energy of the scattered radiation, or what you say, this energy of this energy of the scattered radiation will be less than that of the incident radiation. Since the energy of the scattered radiation is less, so its wavelength will be high. Okay, so lambda incident will be always less than lambda scattered. And the opposite phenomena will happen for anti-Stokes line, that lambda incident will be greater than lambda SC, that is lambda of scattered light. Okay, so you have learned that in the Stokes shift. Uh, so I'm drawing the diagram to understand this clearly. It's a very good question to deal with. Okay, so this is for anti-Stokes. This is the phenomena for Stokes. Okay, so I'm writing it here. So this is the initial state, this is the final state, and this is the virtual state. So for Stokes, this is the Stokes. This is the anti-Stokes line. So for Stokes case, this will be the initial state, go to here, and this will come back here. Okay. And suppose, and for the same, sorry. So for anti-Stokes case, it will go up here, come back here. So if it is lambda incident, and if it is lambda scattered, and here it is lambda incident, similarly it is lambda scattered. So you can see that for Stokes case, lambda incident will be less than lambda scattered. Okay, and where I have written here, and similarly for anti-Stokes case, lambda incident will be greater than lambda scattered. Fine. Now you can see your lambda incident in this case is nothing but lambda y, because you are using yellow laser light. Okay, since you are using yellow laser light, so your okay, so since you are using yellow laser light, so since you are using yellow laser light, so your incident wavelength will be the wavelength corresponding to this yellow color. Okay, so your lambda incident will be lambda y. Okay, so with respect to this lambda y, you can now designate which should be the Stokes line, which should be the anti-Stokes line. So Stokes line corresponding to wavelength, Stokes line happens if the wavelength of the scattered radiation is higher or lower than the incident radiation. This will be greater than the incident radiation. So Stokes line corresponds to something that has higher wavelength than the yellow line. And you can see here that red emission has a wavelength higher than the incident light. So Stokes corresponds to lambda r. And similarly, anti-Stokes line corresponds to lambda g, because I have said here that the incident light has an energy greater, has the wavelength greater than the scattered light. The incident light has an wavelength greater than the scattered light. Okay. So if lambda y is means the yellow color wavelength is your incident, then your scattered will have a wavelength which is lower than the yellow, and lower than the yellow is just a green one. Okay. So you have now finally got your answer. That is, your Stokes line is lambda r. That means your red line, whichever you are going, whichever you are seeing, this corresponds to Stokes line. Okay. And anti-Stokes line is whichever green line you are seeing, it is the anti-Stokes line. So first you have come to conclusion up to this. Now your question is not finally ended. Okay. Now you have to think about what should be the effect of temperature on this question. Will be that what should the fate if y increase the temperature. Okay. Now I have you, if you remember, I have said if you increase T, if T increases, then what happens to the Stokes line's intensity? Stokes line intensity decreases, and anti-Stokes lines intensity, this will always increases. Okay. So if you increase T, what will happen? More number of molecules will be going to the upper state, right? And you can see, okay, let me use another color. Suppose, okay, I am using this color. So you can see for Stokes line, the transition is happening from this one, but for anti-Stokes, this transition is happening from the upper state. Okay. So from anti-Stokes, since if you increase temperature, this state will be much more populated compared to this state. Okay. So your intensity of the Stokes line will get decreased. The intensity of the anti-Stokes line will get increased. Also, in the terms, mathematical terms, I can say that in the lecture number 13, you can also find this, that what I have said here now. So, in the mathematical term, you can say that is the intensity of Stokes by intensity of anti-Stokes. I am writing as a Stokes, which is nu 0 minus nu m whole to the power 4 by nu 0 plus nu m whole to the power 4 into into e to the power h nu m by kbt. Okay. So this was the formula that was also discussed in during the lecture. That is the intensity of Stokes and anti-Stokes line, how they are dependent on the temperature. So if you increase the temperature, so this, if you increase, so this total term will be decreased. Since this total term will decrease, so intensity of the Stokes line will decrease. Okay. So intensity of Stokes line will decrease, but the intensity of the anti-Stokes line, that will getting increase. And what is your anti-Stokes line in this case? In this case, your anti-Stokes line is corresponds to this green line. Okay, this green like thing is the anti-Stokes line. So what will happen if you increase the temperature? If you increase the temperature, the intensity of the green line will increase, whereas there will be a decrease in the intensity for the red line. So your answer, you have to find that the photon counts of the green peak increases. The photon count increases, that means more number of photons are involved here. so the intensity will be much more for this kind of this light. Okay, this is your answer. A very good question. Just using some logic, you can find this answer. Okay, so this is all for this week. Whatever I have discussed about Raman spectroscopy, and I have solved some problems regarding that, and you have learned how to solve these problems. They're very simple questions on the very in the earlier stages, but in the last 3 or 4 questions, there is some logic you need to understand this, and I think you have understood that. So if you have any query, you can ask me in the next assignment or even in the next live session. Okay. So okay. So I am stopping the recording.